aspirant, this question is from GATE 2020, Mechanical Engineering paper set 2, question number 30. A thin-walled cylinder of radius r and thickness t is opened at both ends and fits snugly between two rigid walls under ambient conditions as shown in the figure. The material of cylinder has Young's modulus E, Poisson's ratio V, coefficient of thermal expansion alpha. What is the minimum rise in temperature delta T of the cylinder? Assume uniform cylinder temperature with no buckling of cylinder required to prevent gas leakage if the cylinder has to store the gas at an internal pressure of P above atmosphere. So this is the cylinder that is thin walled. We have to use the formula to calculate the stress in thin cylinder rather than thick wall cylinder. The point that is given here is the cylinder is open from both sides. Stress in the longitudinal direction is 0. That means the cylinder is actually not connected to the rigid walls, but it is only placed between the rigid walls such that it has just snuggled into or fitted between the two walls. There is a gas filled inside the pressure vessel which is exerting pressure P on the walls of the cylinder. So radially outward, this pressure is being applied uniformly on the walls of the cylinder. The cylinder is circular because radius r is given to us, so the cylinder has to be circular, and all along the walls there is uniform pressure P applicable in this fashion. So this pressure P is going to expand the cylinder in circumferential direction, and as a result of this circumferential expanding there will be a contraction lengthwise. From both the sides we can see that the cylinder has compressed. Because of this compression, the cylinder might fall down, or there might be a gas leakage from the gaps that will be present between the wall and the cylinder because of this compression. And that is why the cylinder is heated. Heat that is given to the cylinder creates a temperature difference of delta T. Coefficient of thermal expansion of this material of the cylinder is alpha, that is given. And we have to find out what is that minimum rise in temperature that we have to create so that there is no leakage of gas from this cylinder. That means there should be no gaps between the wall and the cylinder. Strain due to thermal effect, we can write epsilon TH is equal to, it is coefficient of expansion alpha into the temperature difference delta T. Also, if let's say this direction is x and the perpendicular direction is y, we can write epsilon x is equal to sigma x by E minus V into sigma y by E. This is by generalized Hooke's law. There is no stress in the longitudinal direction. Longitudinal direction is nothing but x direction. So this is 0 minus V is the Poisson's ratio. Sigma y is nothing but the Hooke stress that is created due to the uniform pressure P on the walls of the cylinder. So the walls of the cylinder are under stress, and this stress is Hooke stress, which is in y direction. So sigma y is nothing but the Hooke stress. So pressure into the radius, that is the amount of pressure on the cross section of cylinder, divided by thickness. We just rearrange and find out sigma as PR by T. Now as I told you that delta T has to be that minimum value which when applied the cylinder doesn't have any leakage of gas. Now for the cylinder to have no gas leakage, the thermal strain developed due to delta T should be equal in magnitude to the lateral Hooke strain that is developed due to pressure P. So substituting the values, epsilon TH is alpha delta T plus this value from here is minus, don't forget the sign, minus V into PR upon T into E is equal to 0. So from this we can find out the value of delta T VPR divided by alpha TE. Among the 4 options, our answer is option C. To learn more about thin-walled pressure vessels or thin-walled cylinders, you can refer to the NPTEL video Thin-Walled Pressure Vessels, Lecture 31 Part 2, Mechanics of Materials by Professor Saravanan U. He is from Department of Civil Engineering, IIT Madras. I hope this solution will help you clear your doubt. Thank you.